Okay, so we are recording. Why are we, learning these differential equations? I know that we have scientists. You're training to be scientists and engineers and the economists and so forth. Why would we be studying differential equations? Well, differential equations can be applied to real life models. For instance, a tank problem. I'm talking a tank with water in it or brine in it. Let me give you a moment to copy this example down, okay? And then we'll go over the solution. Okay, give you another minute here, and we'll go over the problem. Okay, so in this problem, a tank, and I usually like to underline as I go here. hold on here. A tank contains 20 kilograms of salt dissolved in 5,000 liters of water. Brine, okay, brine's like a salty solution. Okay, brine contains 0.03 kilograms of salt per liter. Okay, that brine enters the tank at a rate of 25 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. Okay, at the same rate. Okay, now, why do we need the tank to be drained at the same rate that the brine's coming in? Or why in this problem are they doing that? That's right, Nathan. The tank, if you didn't do it, if for instance the tank drained at a slower rate than the brine than the rate that the brine comes in, what will happen to the tank over time? It'll overflow. That's right, Sean. And but nevertheless, you know, and also you could have a situation where your rate of flow is faster. Your rate of flow outward is faster than the rate of flow inward. These kind of problems come up in differential equations. They do have uses, but we're going to keep it simple here. So, well, all right. To do this problem, there's more. How much salt in the tank? How much salt remains in the tank after half an hour? So, well, what do we need in order to begin this problem? I mean, what are you used to in math? What are you used to starting with? What do you work with? What do you need?
A drawing.
Well, a drawing, but we also need, how about an equation? We need an equation here. So let's go ahead and try to get an equation. And let's see here. This equation, I notice in the information given to us, it says that brine enters the tank at a rate of 25 liters per minute and drains from the tank at the same rate. So since rate is involved in the problem, what kind of equation do you think we're going to need to come up with here? What type? Rate. What is equivalent for a differential equation? That's right, Jacob. Rates are derivatives. So our equation is going to involve derivatives. All right, so let's go to the solution here, and I'll show you how to do this. So first of all, we have to define some variables. Okay, so this is our solution to our example solution. First, I'm going to let y of t be the amount of salt in kilograms after t minutes. Okay. So y, the variable y, and I choose y because normally, well, I'm used to my dependent variable being called y. Y is a function of t. So the amount of salt after t minutes is equal to y. And in the problem, they're saying the question was asked, how much salt remains in the tank after half an hour? Well, that means we have to try to figure out what y equals. Okay, what is, and when I say y, of course, I mean y of t, right? What is the solution to that? Well, first, we have to come up with a differential equation. dy dt would be Well, the units are in kilograms, and time is in minutes. So the rate of salt flow with respect to time is dy dt. And in this problem, we have briny solution coming in, contributing salt to the solution, but then remember the tank had water in it. So the brine mixes with the water, and then a solution comes out of the tank. So dy dt is going to be rate in minus rate out. The question is, what would the rate of salt coming in be, and what would the rate of salt going out be? Well, here's where, keeping our units when we do our work is helpful. So we're told that the briny solution enters the tank at a rate of 0.03 kilograms of salt per 1 liter. I'm sorry, I said that wrong. The concentration of salt in the brine is 0.03 kilograms per liter. How many have seen concentration in chemistry problems? Okay, all right, quite a few of you, Tall and Sean, and I'm sure you remember that from your high school days, right? So concentration of the brine coming into the tank is 0.03 kilograms per liter, but it comes in at a rate of 25 liters per minute. So if we take the concentration of the brine and multiply it by the rate that it's coming in, we find out that the rate, because here the liters simplify out, we find that the rate of flow of salt coming into the tank is 0.75 kilograms per 1 minute. Okay, how many find it helpful that I'm writing the units in here? Is this helping you? All right, Tall likes that. Excellent, excellent. And Samuel, good, good. And it helps you just, you know your units for your differential equation have to be in kilograms per minute. So I know I'm on the right track because my units for rate in are kilograms per minute. Now the rate out, okay, here's the thing. So the solution, the solution in the tank is mixed up, okay, and the tank always has 5,000 liters. So the concentration of the solution would be equal to whatever the salt content is at time t, okay, which is y of t, divided by 5,000 liters. Okay, so the concentration of the solution leaving the tank is variable. Okay, it's a function of t, function of time. Okay, so it's y kilograms over 5,000 liters, but then that concentration, that solution going out it flows out at a rate of 25 liters per minute, and hence rate out is y kilograms per 200 minutes. Please let me know if you have any questions. All right, are we ready to go to the next page? Okay, Samuel's good. Tall's good. Does anybody need more time? Jacob's good, excellent. Abadar is good, wonderful. Okay, well now what we're going to do is we're going to take the rate in and the rate out, and we're going to substitute them in the differential equation here. So we do that, and we end up getting this. dy dt equals 0.75 minus y over 100. So I'm not worried about carrying the units anymore. I know that the units are correct. So we had, you know, 0.75 over 1, right? This was the rate in, and the rate out was y over 200. Okay. So now we have a differential equation that we have to solve. And it helps when we solve this differential equation if we can get a common denominator. Well, the denominator between 1 and 200 is a 200. So I can rewrite the right-hand side of the differential equation as 150 minus y over 200. And I do that because it just helps me separate the variables a little easier. Please let me know if you have any questions. All right, well then we go ahead and we separate the variables. So generally I like to have my y variables on one side, on the left side. So what I'm going to do is I'm going to multiply both sides. Let me just clear this. I'm going to multiply both sides of this differential equation by 150 minus y. And I note that y cannot equal 150. And actually, it will never equal 150. And you'll see why towards the end of the problem. Whenever you divide by a variable, you can divide by a variable so long as you know the denominator. Well, I want to be careful here. The denominator can't be equal to 0, okay? And ours is not. But okay, so when I do that, I get here, and now the variables are separated. Variables are separated, and I'm going to integrate both sides of the differential equation. It's an absolutely beautiful process. All right, and let me know when you're ready to go to the next page. Obviously, what we have to do is integrate now. Maria's good. By the way, class, on the left side, obviously the left side is harder to integrate. What integration approach would you use on the left side? I like that, Renat. I would use a substitution as well. Okay. Well, on that note then, if everybody's good, I'll go to the next page. If there are no questions. Okay. Well, so we're going to let u equal 150 minus y. Then du is negative dy. Let me just put in kind of an extra step here. So u is 150 minus y. That means du dy is equal to negative 1. Right? So that means then that du is negative dy, or negative du equals dy. That's how we get here. And so now the integral on the left becomes an integral with respect to u. And the integral on the right, I factor out 1 over 200. The antiderivative of 1 over u is the log of the absolute value of u. You have to remember the absolute value. Now what happened is on like when I did the integration, as you know, the left-hand side is going to have some constant. The right-hand, call it C1. The right-hand side is going to have some constant, call it, well, I want to be a little careful how I phrase this. We know there should be like a, say like a, plus K1 here, right? And then, we have a plus K2 here. But you know that you can subtract the constant on the left to the right. And so it's okay to go from this step to this step. We know this constant C1 results from combining the constant on the left side with the constant on the right side, and so it's okay. But I know I'm going to have to manipulate my constant of integration, so I don't call it big K. I don't call it K yet, or little k. I don't call it K yet. So of course we want to get the u by itself. So I'm going to multiply through by -1 on this equation here. I'll multiply through the whole equation by -1. And then that's going to give me this equation below. And the negative C1 I'll call C2. You see how I do that? And so I have now the log of the absolute value of u equals -t over 100 plus C2. But I want to get the absolute value of u by itself. So I'm going to do what's called exponentiation. Samuel, question?
So the C2 is just a placeholder for negative C1?
That's correct.
Oh, okay. Thank you.
That's correct. Good question. Good question. So if I exponentiate both sides of the equation, I end up with this equation. But what is e to the power log of absolute value of u? That's just absolute value of u. Let me know if you have any questions on the math that you're seeing here, okay? Tal, question?
Is there a reason why we don't just add C at the end? Like, is there a reason why we're changing it so much?
Well, it's because it is getting changed. I mean, here, good question. Here, let me just phrase this. If you have e to the a plus b power, that's the same as e to the a times e to the b power, of course. Those are equal to each other. And this e to the C2, well, I can't just call that C2 because it's not equal to C2. It's equal to a different constant. Okay, I'll call that C3. It's just it's the way you have to do it because mathematically it's correct. I can't say that e to the C2 equals C2. I can't do that because it's not true. Maybe for one value. Good question. Does that make sense?
Yeah, could I just to understand, is the reason why this is done differently than how we did in the past because we do extra math after we do the integral?
Well,
Like, because in the past, after we take an integral, we use just the constant. But is it because we're doing more math after the constant on both sides of the equation?
that's correct. We're doing more math, and that math is causing that. We're tweaking every time we do a math step, we tweak the constant, we change it, and so that's right. And I don't want to carry around the constant e to the c2 power. I don't want to do that. So I just replace it with, I just rename it. I rename the constant as as c3. But that's right. We're doing more math, and when we do the math, we are adjusting the equation, and so that brings up new constants. This e to the c2 is not a constant of integration. The constant of integration was c1. That was your constant of integration. But, you know, we have to solve this equation for u, and so the math that we do to the equation affects the constant, and it's always changing it. Very good question. Very good question. All right. Are there any other good questions? What do you think we should do now? I have the absolute value of u, but ultimately, what am I trying to solve the differential equation for? What variable am I trying to solve for? Is it u? Well, t is the independent variable. Samuel?
You're
Good,
solving
LePage.
for, yeah,
Solving for y.
yes.
Excellent, excellent. So what do you think I should do with this u variable? What might be a good step to do now? Am I kind of done with you? Can I, what should I do now if I want to, you know, get to y?
Divide both sides by u?
Well, what's u equal to again? 150 minus y. And Nathan says plug 150 minus y back in for u, and that's correct. That's correct. And that's what we do here on the next page. Here's the equation, right, that we had. And I'm going to replace u now with 150 minus y. I still have the absolute value there, but it turns out that 150 minus y is always going to be positive. I'll justify that at the end here, but it's always going to be positive. So we can drop the absolute values. Well, actually, hold the phone. Hold the phone. I don't want to say that actually. No. Let me do this. Let me do this differently, because I want to do it kind of like example 3 does it. You see, books treat things differently. You don't know for now. You don't know for now that 150 minus y is greater than 0, but I'm just telling you. But you know, let's talk about this plus or minus. Where's this? You know, where'd that come from? What happened there? Where'd that come from? Well, okay. Let's think of an analogy here. If you had the absolute value of a equals 3, what's a equal to?
Positive or negative 3?
Good. Positive or negative 3. Okay. If you had the absolute value of A equal to a peach? What's A going to be equal to?
Plus or minus the peach.
That's right. Good, Sam. Well, what I'm doing here in this step is no different. So I'll just take off this little red circle. The C3 times e to the negative t over 200 power, I'm treating that like my peach. And the absolute value of 150 minus y, well, or the 150 minus y, that's like my A. I'm taking the absolute value of A, and here's my peach here. The absolute value of A is equal to my peach. A then is just plus or minus the peach. So this is why I have a plus or minus in front right here. Okay, C3 is still there, of course. Now the thing is, are there any questions on this step? This step here. Is the peach analogy helping? How many found that helpful? Was that okay? Michelle likes it. Good. I'll take it. If it helps one student, I'll take it. Well, now let's think about what we got here. Let's think about what we have. We have plus or minus this C3 times e to the negative t over 200. But I could just equivalently, I guess what I'm trying to say is this. Let me phrase it another way. I'll put it in blue. The plus or minus, no, let me put it up here. The plus or minus C3 times e to the negative t over 200 power is the same as plus or minus C3 in parentheses times e to the negative t over 200 power. Well, this plus or minus C3 is a constant. It can't be both plus or minus, it's one or the other. So I can replace plus or minus C3 with C. And you notice I don't have the C, I don't have that C number. I'm not calling it C4. Okay? I'm not calling it C4. Because now I know that's like my final altered constant. So I'm just going to call it C. And now I proceed forward and solve for y. And it turns out that y will equal 150 minus c times e to the negative t over 200 power. This is the amount of salt in the tank at time t. But can I find, given this solution for y, can I find how much salt remains in the tank after half an hour as it stands? Is this a useful equation, a useful solution right here? I mean, it's useful, but does it have everything I need to answer the question? No, because what's in there? We have a constant in here, right? Good, Tao. Good. Hold on, I forgot who chatted that. One moment. Well, thank you who chatted that. Thank you, Tao. Thank you, Sean. Yeah, I have I want to solve for that constant C. So I have an initial condition. We were told that the tank contained, the tank contains 20 grams of salt. So at time 0, the salt content of the tank is 20 kilograms of salt. So I can use that initial condition to solve for that constant C. And that's what I do. That's what I do here. So y of 0 equals 20. I substitute in 0 for the t. And I'm able to find that constant equals 130. And therefore, my y of t is 150 minus 130 times e to the negative t over 200. Now I have a formula that tells me how much salt is in the tank at time t. I have a formula now. Please let me know if you have any questions. Okay, hold on. One moment here. Yes, Nathan?
In the first equation that you have circled in blue, you have 150 minus CE raised to some power.
Right, raised to the negative t over 200th power. Yes, yes.
So what if I just didn't like negative signs? Could I just change it to 150 plus C E raised to the negative t over 200? I called it a different name.
You could, yeah, the minus C, you could call it like, I see, like plus K or something like that. Yeah, you could. But then the K, your K would be a negative 130. You're gonna end up at the same solution. But you could do that. It's sort of it's kind of an extra step, but you could do that. Good question. Good question. Are there any other good questions? Let me ask you this. Well, now we got to answer the question at hand. But if we were to graph this, okay, maybe let me just bring up the ebook. We're actually doing example 6 here. So let me bring up the ebook real quick, and we'll answer the question here. But let me. This is a mixing problem that we're doing. Here's a picture. Let me just see here. One moment, class. Yeah, this is a picture of our solution. At t equals 0, you notice the salt content. So the red graph is our solution. Y of t equals 150 minus 30 times e to the negative t, y of t is 150 minus 130 times e to the power negative t over 200. So the salt content, what did it start at? Like if you look at that graph in figure 10, at t equals 0, what's the value of the red function of our solution at t equals 0? 20. That's right, Renaud. We're starting out with 20 kilograms. Okay, and what's happening to the salt content over time? It's increasing, but what does it seem to be approaching over time? They have their, what, 200 hours, 400 hours? That's right, Nathan. It seems to be approaching 150 kilograms. So the salt content of the tank over time seems to be approaching 150 kilograms. And there's a reason for that. Okay. But let's go back to the, let's go now back to the example here. Hold on. Well, we're working out example 6. So here we are. Here we are. And now, to find out, we want to find out, by the way, what are the units for T? What are the units for T?
Minutes.
Minutes. So, all right, and we want to find how much salt remains in the tank after half an hour. So I want to find y of what? What number am I gonna put in here? Am I gonna put in a half?
Oh, it's in minutes. It's in 30.
That's right. Good. So we're gonna compute y of 30. And that's what we do. So we have to be consistent with our minutes. And you got to be careful. WebAssign will try to trick you sometimes a little bit. They'll have units in minutes, and then they'll say, hey, how much is left after 2 hours? You know, and well, after 30 minutes, the amount of salt is 38.1 kilograms. So the salt in the tank is building. It's building. This briny solution's entering the tank, and as time goes on and on, the solution in the tank is getting more and more salty, which kind of makes sense, right? Because you know you're replenishing the tank with this brine, right? And it's salty, so the tank should get saltier. Now, as t goes to infinity, okay, how much salt is going to be in the tank? Well, we look at the limit of y of t as t goes to infinity. This e to the negative t over 200, that's going to go to what? What's that go to as t goes to infinity? That should be an easy one for you all. Good. It goes to 0. Good, Renaud. Good, Jacob. And that leaves you 150 kilograms. And that confirms the figure 10 from example 6 that we saw in the book, section 7.3. The salt content of the tank does eventually approach 150 kilograms. It reaches what's called an equilibrium. Okay, it reaches an equilibrium. And it makes sense over time because, remember, we have that concentration in the tank. Well, I want to be careful here. Yeah. So this makes sense as over time we have that the concentration in the tank approaches 0.03 kilograms per 1 liter. Because we keep pumping that brine into the tank, so that the tank eventually is going to be a tank. The tank's going to take on the characteristic of the brine over time. Okay, it's like well, I want to be. I honestly, I can't really think of a. I was going to try to think of an analogy, but you know, it's like taking a well, trying to think. How many have had like Nesquik before, like that, you know, that powder that you put into milk? And okay, Jacob likes it, Tal likes it, Sean likes it. Yeah, so imagine, like, you know, constantly putting Nesquik in your milk, but the glass, like Nesquik solution in your milk, but the milk empties too. You mix it and it empties, and eventually you're gonna have Nesquik solution. I don't know if that's probably not a great analogy. I don't know, but at any rate, the point is over time, the tank is going to take on the characteristic of the briny solution. The tank's still going to have 5,000 liters, but if you take 5,000 liters and multiply by 0.03 kilograms per liter, which is the concentration of the brine, look at this, you get 150 kilograms. And by the way, it doesn't matter initially how much salt was in the tank initially. It's irrelevant. The initial amount of salt in the tank is irrelevant. Okay. Are there any questions on this problem? Who thinks this is pretty interesting? I'm just kind of doing a survey here. All right, Tal likes it. Jacob likes it.
The final answer is 150 kilograms.
Sorry, Samuel? The answer to the question, how much salt remains in the tank after half an hour, that's 38.1 kilograms. But I wanted to sort of justify to you that figure, you know, in the textbook, that figure 10, and that's why I have all this below. But we answered the question up here.
Okay, thank you.
Okay, you're welcome. Are there any other good questions? Okay, I'll stop the recording.